Hello, everyone, and welcome to today's webinar. My name is Margot Newcomb. I'm the Director of Marketing at Teledyne Marine, and very happy to have you joining us today. Our topic for today is going to be an introduction to our BlueView ProScan software. This is the second in a three-part series that's dedicated into taking a deep dive into our 3D BlueView sonars. Today, as usual, we have our tech gurus, John Robertson and Tyler Whitaker here, and they're going to be walking you through this powerful software program, providing you with tips and tricks to ensure that you collect the best data possible. So for those of you that have not already met John and Tyler, just a couple of details. John is our customer service manager here in the Americas, and Tyler is an applications engineer. And I know they are both looking forward to getting back out in the field with all of you and getting to see the cool projects that everybody is working on. So hopefully we're getting close there. A little housekeeping. I know a lot of you guys are repeat, so you know the drill, but we are recording this session and it will be available, and we will be sending it out to you within 24 hours via an email. And also everyone is muted, but we are looking forward to doing some Q&A at the end of this period. So as we go along, please do type in any questions that you have for John and Tyler, and we will address those at the end. So without further ado, I'm going to go ahead and hand this over to John and Tyler.
Thanks, Margot, for the introduction again. We'll save everybody from personal introductions, details. You can follow up with the previous recorded sessions to get some of that, but we'll jump right into it because this is going to be a more in-depth training on the software. So we'll hand it over to Tyler to begin with that session.
All right, thanks, John and Margot. Yeah, so today we'll just jump right into it. We're going to be reviewing the ProScan software, which is our primary 3D software acquisition software for our BV5000 product. Let me share this. And I will ask the usual question of, can you guys see my screen? I guess the people
that's
okay.
The proper
great
view.
Going to be jumping back and forth between PowerPoint and the software, primarily going to be spending most of our time in the software like we did with ProViewer, our 2D software a few presentations ago. So bear with me throughout the PowerPoint. There's not much of it. So we saw this slide last time. This is kind of our software workflow for the BV5000 scanning product. First step here, we do have ProScan, which is what we're going to be discussing today, as well as blueview, simple point cloud viewing software. Next week, we're going to jump into the point cloud registration, cleaning, post-processing, editing, all that fun stuff. So that is going to be with QuickStitch. Again, there's many options, but I will be using QuickStitch. And again, that will be last week, which will be the last kind of video, last webinar in the 3D series. So, but ProScan is arguably the more important of the two. It's the main acquisition software. It's going to connect to your sonar. It's going to actually generate your XYZ point cloud, and basically give you the data to process with your point cloud processing software. The most important, I guess the biggest hurdle a lot of new users have with our sonar in general, or any sonar really, is really interpreting what you're seeing in your live view. So as you recall from last week when we went over kind of the BV5000 hardware, this is kind of a vertical 1 degree swath. So it's a small slice of your environment you're looking at in the live view. We can see here the actual 42 degree vertical swath. Again, it's 1 degree kind of horizontal. And we're manually panning that around the environment to build this point cloud. So until we have the point cloud, until we've completed the scan, we're really just getting this view in our live view, which is simply a slice of the environment, in this case of a bridge footer. So it's important to understand what you're looking at in the live view. As you use the system more, this view actually can be of benefit to you. sometimes just as much as the point cloud. However, ultimately people are looking for the point cloud, right? So, but this is really what we're going to kind of be looking at today a lot in our actual live acquisition view. Let me actually jump out of this. So I'm going to just go right into the software here. Let's see. Actually, let's do this one. Okay, so here is our main kind of UI we're looking at. So this is a playback SON file. This is a file that's was recorded 2016, it looks like. So again, just like with ProViewer, when you play back a file, you get a couple sliders here at the bottom, play, pause. You're getting this similar kind of copper hue data that we got with ProViewer. And again, you're getting just a slice of the environment. So right here, just right off the bat, we can tell, okay, this looks like the seafloor, this looks like an object of some sort. So as I press play, we're going to be playing through the scan. So if you can picture this kind of vertical swath scanning across the environment, that's what we're going to be seeing here. So we can see that object come out of view as we scan past it. We just have plain seafloor here. That's the end of the data set. So this is really all a scan is going to look like, really, when you're actually playing it back. It's just a simple slice of data as the sonar actually scans around. So a couple things on the UI here. We have range sliders. So just like if we were connected to a live sonar, we have the ability to change the range of the sonar. Same thing goes for playback. If we wanted to kind of bring in the focus, I guess, so to speak, we can decrease the range to really only create the point cloud based on points closer to us. If we really want to ignore the kind of longer range data, we can adjust both the maximum stop and minimum start ranges. So if we wanted to ignore, say, the first 5 meters, we could set that here on this start slider on the left here.
So one important thing to add to the range sliders. So if you set up a scan from the beginning, you deploy the tripod down to the seabed and you start your scan, the recording will only record data based on where those range sliders are. So if you drag down to the max range, the stop range down to where Tyler has it now, 16 meters, it'll only record data from the sonar out to 16 meters and disregard any data past that. One thing that will change also is the ping rate itself. So if you have the sonar set to max range, the max stop range of 30 meters, sound is going to take longer to go out and back. So you may have 5 to 8 pings a second at max range. But if you bring that down to a shorter range, your ping rate will increase throughout that as well.
All right, you guys see my screen still? See ProScan?
ProScan, yeah.
Okay, I just swapped screens, so I'm not looking away from the camera. Yeah, that's absolutely right. And we'll actually have an example. The last thing we'll do today is an example that really shows how changing those range sliders affects the data. So just continue to go over the UI here. A few other things like ProViewer, we have our ping rate, changing the range sliders and a recorded file isn't going to change the ping rate, obviously. Connected to a live sonar, that's when John mentioned changing the range will actually affect the ping rate, but right now it's not going to do anything because it's already recorded data. We have a timestamp here. This was not recorded in 1970, but that's just a default. The actual sonar model, MB 1350, and then the sound speed, which we'll talk about in a bit. Sound speed, quite a bit more important for the 3D system than the 2D system. So we'll talk about that. Over here on the right, we have 3 settings: intensity threshold, detections per beam, and separation distance, which is tied to detections per beam. These kind of help you set where the software wants to basically specify what kind of threshold you want the software to pick a point at. So I'll just show you as an example. Intensity threshold by default is 250. If we look closely at the screen, we can actually see the copper data, obviously, but we can also see little white dots. It's probably most clear up here on this either chain or rope or it's noise, whatever it is, it doesn't matter. We're seeing a lot of white dots here. So if I were to increase the threshold, basically increase the level of intensity of return for the software to pick a point, it's probably going to eliminate those points. Yeah, there we go. So if I set it to 5,000, I'm bringing that threshold way up, meaning that the returns have to be incredibly strong for the software to say, yes, I'm going to pick a point there. The returns off of whatever this is are not strong enough to exceed that threshold, therefore they're eliminated. So you can see there's little visual cues in ProScan, little white dots that tell you, basically the software telling you this is where I intend to pick a point for my point cloud I'm building. So threshold of 5,000 is very high. I recommend most new users just stick with 250. And main point here is all of these settings on the right, I wouldn't really bother with. I would leave at default during acquisition. I would really just play around with them on playback, because you can play back the file infinite number of times and generate infinite number of XYZs with different settings. And it's just much easier in the office rather than on a boat or, you know, in outside conditions.
Yeah,
so that's
all those settings are not affecting the raw data that's being collected. So the .son file collects all the raw acoustic data, and those are settings that can be adjusted afterwards. And as Tyler mentioned, post-processed with different intensities or beam point selections.
Right. Yeah, and here's kind of a visual on that intensity threshold. So we can see the setting. These are all a bunch of intensity returns. So the higher the intensity threshold setting, the stronger the return needs to be for the software to pick a point there. A good visual example is here. We can see 2 point clouds. One has a threshold of 1,000. One has the default threshold of 250. Lots of bubbles or fish or something in the water here. So at the default setting, you're getting an incredibly noisy point cloud, whereas just simply increasing the threshold, it really cleans out a lot of the noise, but still gives you returns, the strong returns off the concrete wall or whatever it is we're looking at here. So really useful setting to kind of tweak what kind of data you're getting.
And you'll want to be careful though, because especially if you look at that example again, the wall itself, the flat wall, if you go too high on your threshold setting, you could start eliminating actual data, not just noise in the foreground. So if you look, can you point out on the left-hand side of that, on the wall, the picture at the bottom? Yeah,
here?
You see how it's starting to eliminate the data on the left-hand side of the yellow section.
Yeah, you can kind of see over here.
Right.
We're missing some data. So yeah, it's there's kind of a perfect setting. So it might take trial and error or really looking at the raw data itself to determine what the magic number is. So yeah. Other setting here is multi-detect. One thing I'll say about this is absolutely, generally under any circumstance, do not use this during acquisition. I found it really slows the computer down. So I would really only play around with this after, during playback. Same with the threshold, but this is even more important to do after the fact. So it's basically every single beam, every one of the 256 beams of the sonar are going to pick the one strongest return along that beam. That's just the default setting. Typically that's good for most imaging applications, but if you have multiple detections along one single beam that you want to have returned in your point cloud, we can use this multi-detect. So pretty straightforward. If we wanted, say, 2 detections for each beam, it's going to pick the 2 strongest returns along that beam, all the way up to the 10 strongest detections. So just right there, you can see how many points I'm now getting. In fact, it's huge excess of points. This is going to be an incredibly noisy, really unappealing point cloud. And I've never really needed to use 10 multi-detects. So that's kind of excessive, but you can kind of see the example if it's picking the 10 strongest points along each individual beam. So 256 beams times 10 points per beam, 200, is that
Per
math?
pane, yeah,
Yeah,
it's quite
that's
a bit of points.
Yeah, so good to keep in mind as a tool in your toolbox, but I would usually just stay a few detections per beam. This is really just if you're looking at your point cloud and you're saying, oh, I have that object in the foreground that I also wanted to pick up in addition to the object in the background, maybe your structure. If you want to pick both, you can try setting that to 2 and rerunning it to get more points. Generally, you're going to have more cleaning of points the higher detections per beam. And separation distance is tied to that. It's basically the minimum distance needed for the software to pick another point along that beam. So say you have your 2 points, 2 detections per beam you're picking. This basically says they have to be 0.1 meters, at least 0.1 meters apart. If they're closer than that, it won't consider that another valid detection. So another setting just to kind of to play around with, and you can see, again, you can see the live view update as I actually change this. So good kind of settings you can do. You can do well live, but I recommend playing around with them in post-processing. So let's jump back to the PowerPoint. Actually, you know what? Let's jump into another data set here. Okay, so this is actually, if you were here last week, we went over a complete 3D data set that was taken in Chicago. It was actually taken by John here. Tripod deployment. I'll show the point cloud really quick. So I showed this last week. This is a resulting point cloud of 3 locations, 4 locations maybe. So this data set is actually the raw data from that collection, from one scan location, right? Not all 4. So I just want to review a few things on this, again, with the post-processing. So if I were to collect data, in this case in Chicago, find that a setting is wrong. Maybe I didn't want my range out too far. Maybe my sound speed was wrong. The benefit of playing back data is that you can change all of that. So if, for example, let me progress this so we're looking down. So here we're looking at the seafloor or whatever, the river bottom in Chicago. Say, for example, I don't care about anything beyond 10 meters. I can then, after the fact, decrease to closer to 10 meters, say 11 meters. I can also, in this case, this is actually important, I can change the sound speed. So up here at the top, this kind of red wedge will bring up this sound speed slider. So briefly on sound speed, as mentioned, it is more important for the 3D system generally because the 3D is used for slightly more accurate measurements, more kind of quantitative look of the surrounding area and the seafloor. So sound speed kind of plays into that quite a bit more. It's not, I would say, as important as like a traditional multi-beam surface vessel mounted, but it all depends on what you're doing. Like I have said dozens of times, it's very application dependent. So if you do require highly accurate measurements, we do recommend getting at least a temperature of the water or really having a sound velocity probe on board that you can stick in and really get an accurate sound velocity. So if you have neither of those, a good kind of trick to do, if we look at this data set, let me just kind of scroll here. So we can see if we cut down the middle here, we can actually see on the seafloor, there's kind of a break. So we generally know that that's probably not real. This should be a nice continuous line on the river bottom here. But we actually see a break, and that break is right down the middle of the sonar. So almost always that's going to indicate that your sound speed is wrong. It's not correct. The physics of the sound are not matching up with how the software is representing the data. So if I pull up my sound speed slider, I can really actually slide it around to change it, and it will update the image real time. So if I go up to 1546 meters per second, that's clearly not right. That's actually much worse. We can see the break getting larger. If I were to go down to, it's Chicago in the fall or winter, so it's going to be much colder. So if I were to go down to 14, getting closer, we'll say there, 1445 meters per second looks pretty well where they're lining up, actually probably a little lower. So just like that, I've kind of estimated the sound speed, probably within 10 to 15 meters per second, plus or minus. So kind of quick and dirty way to do it. But if you don't have temperature, if you don't have any probe to determine sound speed, it's a good way to do it just after the fact. So, and that was a good thing to demonstrate because this data set was collected at, I think, 1500 meters per second or 1480, some incorrect value, which is fine because after the fact, what I'm doing here is I'm just changing it to the correct sound speed, clicking OK, and then I'm clicking in the lower right here, scan. So this is our playing back the scan and post-processing after the fact and regenerating the point cloud. So again, just clicking the scan ... It comes up with a little window here that I'll briefly go over. So check by default, generate 3D point cloud. That's generally what we want to do. So I have that check marked. We just say where we want to save it. Usually I will call it maybe the same file, Chicago, and then call it reprocess with correct sound velocity, something like that. Just to label it so I know what we're doing. Don't show images. Basically, it's going to not update the image in the background, just makes it faster to regenerate the point cloud. All these other settings, not as critical. There is a way to apply, say you have an X and a Y position, you can apply that to the point cloud. You can apply a heading, a depth, you can kind of apply all this if you have it, and it will actually change or correct the point cloud based on what you input here. So if you input an X and a Y value, the center of that point cloud is not going to be 0, 0, 0. It's going to be X, Y, and Z, whatever you specify. So if you do want to kind of move the point cloud around, that's a way to do it. Otherwise, what I recommend is just doing that in your actual point cloud post-processing software. So quick stitch, cloud compare. It's going to be much easier to move and manipulate the point cloud than trying to do it by specifying an X value here. But there are certain applications where these things might come in handy. So, and then you just go ahead and click Start Playback, and it will start running through the data set. You can see at the bottom here, we're running through the data set. What it's doing right now is actually compiling that point cloud. In the interest of time, I will not let that play.
I wanted to touch on sound speed while we were here. So the sound velocity, if you, well, to pre-answer any questions about sound speed and having a sound velocity probe or a profile, the ProScan software is not designed to take in a live sound velocity or a profile. To go into that kind of application, we would essentially get into like the survey grade software, which the BV5000 can integrate into, for example, Teledyne PDS software to collect data from that application, and you can input profiles, live sound velocity, position, heading, motion sensor information as well to collect data that way. But in this application, ProScan, we do not take in those external sensor live data streams.
Yeah, that's a really important distinction to make too, just in that ProScan certainly is not survey software in any way. It's meant to work with the BV5000 and only with the BV5000. That is the sonar and an ROS pen until scanning the environment. that's really it. There's not a lot of other functionality in ProScan, so that's where yeah, like John said, PDS comes in handy, or HiPack or whatever you're using. Okay, so yeah, once I play back the file, immediately after that playback is done, it should actually pop up with a point cloud. Is this it? That's not the right one. Yeah, so it'll pop up with the point cloud that it just reprocessed. In this case, this is actually the point cloud. If I were to let it finish playback, it would say, here's your new point cloud with the correct sound speed with changed maximum range. Of course, this point cloud still needs cleaning, which will be next week. We can see a lot of surface noise here, but we have the correct sound speed. We don't have a break in the bottom. If we were to not change the sound speed, we would likely see an artifact in the data. We would see kind of a ridge on the bottom. We don't have that. We have a nice smooth ground. So good review after the fact. Point cloud pops up. We'll go into blueview in just a bit here. But that's basically the overview of playback, replaying a file to regenerate a point cloud. Now, if I were to be connected to a live sonar, live pan and tilt, we get a very similar menu to this, but a little different. So I do want to spend some time on that. Because I'm not connected to a live sonar, we have to depend on a slide. So let me go over this first. So if I were connected to a live sonar, instead of that scan ... we would actually have, down here, we would have pan and tilt controls. Actually, there's a slide of it. Here we go. So this is actually a screenshot of a live view. So if we were live, we would have pan and tilt controls. We would have the same kind of raw image. And we would have the start scan button down here. It's hard to see, but it says start scan right below the pan and tilt controls. When we click start scan, we get this big window that comes up. So there's a lot of really important settings here for first-time users and just for any users. That this is really important because a lot of these settings you can't change after the fact. You can't change the fact that you only took a 90-degree scan instead of a 360-degree scan, right? So
can you expand the window?
Oh yeah, that better?
Yeah, that's good.
Okay. Yeah, so scan type. There's two different types of scans, a single and a spherical. A single is just essentially a one-off scan at whatever tilt angle you happen to be set at. It's going to do a scan at that tilt angle. So for example, if you tilt up, say 3 degrees, and you're pointed up at your structure or whatever you want to look at, and you do a single scan, let's say you do it at 360 degrees, it's going to do one scan 360 degrees at your, what did I say, 5 degrees up. Just a single one-off scan. Spherical scan, I'm gonna exit again. So spherical scan is basically kind of an automated way of doing that. So if you do spherical scan, you can specify these tilt angles. Only 4 different options: plus 45 degrees, 15, minus 45, as pictured down here. So if we do spherical scan and we check mark all 4 tilt angles and we do 360 degrees, it's going to be quite a long scan, because what it's going to do is it's going to do minus 45 full spin, and then it's automatically going to go to minus 15 full spin, plus 15 full spin, plus 45. So 4 different tilt angles, pretty much the entire water column. And after the fact, it's going to actually put all of those point clouds together into one point cloud. That's, again, a spherical scan of the entire area. So if you really want kind of an easy setting and you're in not very shallow water, spherical scan is a good thing that a lot of newer users or more experienced users generally use, because it's kind of more of a one-click automated tool function. I do want to say, if you are in shallow water, say less than 5 meters or even potentially less than 10 meters, this might not be the right choice because plus 45, you can imagine, is looking up at the surface. That's going to generate a very noisy point cloud, just a point cloud that's mostly surface reflection. So,
and that can be deselected too, right? So if you select spherical scan, you can you see the tilt angles where you're pointing. You can select one or all four of those. And to answer the question of how long does it take to scan, if you did a spherical scan at 1 degrees a second with all 4 tilt angles, that would be a 24-minute scan at that one location. And then if you deselected plus 45, for example, that would subtract 6 minutes from that scan time. And you can, depending on the requirements for data density and accuracy of the details of the data itself, you can increase the scan speed to reduce the amount of time it takes to scan in those locations too, as well as the pan angle. So
yeah, and that's the segue into the next bit here. So last thing on the scan type is basically if you want control over where your tilt angle is, I would recommend using single scan. If you're okay with these fixed plus 45, 15, minus 45 degree tilt angles, definitely use the spherical scan because it does just make things a little more seamless. And then also puts all the point clouds together. So
they'll be recorded in the same .son file and XYZ file automatically if you do the spherical scan. However, if you do a single scan in the same location with 2 different tilt angles, it'll generate 2 separate point cloud files and 2 separate .son files that would need to be merged together later.
Right. As we have kept mentioning, pan angle is just how much you want to look at. So 360 degree is mostly where people land. It's going to give you data of the entire environment around the sonar. The only reason you would want to use less is maybe you want to minimize your time post-processing. You don't care about what's behind the sonar, you only care about what's in front. Also, if you're in kind of rough environment, you need quicker scans. You don't really have time to do full 360, and you, again, only care about what's in front of you. That's where 180 might come in handy, maybe 90. I've never used 45 degrees, so use that at your discretion, but most people generally stick to the full 360, time permitting. And then speed, brief note on speed, it goes I think half a degree all the way up to 10 degrees per second. I generally stick around maybe 1 or 2 degrees for the highest quality of data. Half a degree per second, in my opinion, is actually too slow. It really it gives you way more data than is needed. You know, the sonar's pinging anywhere from 20 to 50 times per second. So you have a lot of pings, you have a lot of data, and slowing it down to half a degree a second is just too much, in my opinion. So
yeah, usually I agree. I don't think it really adds that much more resolution to the data itself. It might even be a nuisance with noise.
Yeah, yeah, absolutely. I do use the 10 degree per second occasionally. I mentioned this last week, but I call it a recon scan. If you drop the tripod kind of blindly, don't really see where it's located, and want to do a quick 10 degree per second scan to make sure A, your tripod's not falling over, you know, and B, that you're really capturing what you want to capture, whether it's a piling or a key wall or anything like that. So quick scan, 36 seconds if you do a 360 degree, and then that kind of confirms, okay, I'm in a good location, let's slow it down to 2 degrees per second and do a higher accuracy or higher data density scan by slowing it down. This button, center scan at current pan angle, is really only applicable when you're doing anything less than 360 degree pan angle. So if I were to do a 180 degree scan, then the question comes up of, okay, where's the center of my 180 degrees? If you don't have this check marked, what the sonar is going to do is it's going to go back to its 0 point, and it's going to use that 0 point as its center of the 180 degrees. So if your actual structure is behind you, is say at 100 degrees, and you don't check mark this box, but you want to just capture that structure, it's actually not going to capture it because it's going to use the 0 point as your center. So generally, if you're not doing a 360-degree scan, you're pretty much always going to want to have this check marked, because what it will do is it will center its scan in this example at that 100 degrees. So it will center the scan right where your structure, your object of interest is, and it will make sure you capture that whole object. So again, only applicable if you're doing less than 360, and it really just tells you where the center of your 90 or your 180 or your 45, where the center of that will be. File naming, important to keep your files organized. Probably the most important thing I tell people by far is be organized, because if you go back and you don't know which scan is from which scan location, it can make post-processing and registration an absolute nightmare. So like I said last week, have a scan plan where you basically draw locations on a map where you intend to drop the tripod or otherwise deploy. And then name your files based on that location. So, name the file location 1, scan 1, or location 2. And it will really kind of help you piece it together when you're actually doing the registration. So
if you're just doing 1 or 2 scans, it's not as important, but when you get a big structure, when there's 10, 15 scans, it really comes into play and helps you keep it organized when you're doing the registration together.
Yeah. So very important to keep organized, especially if you have a big structure, a lot of locations.
So again, a quick note for everybody, if you have any questions, we're getting close to the end of our time here. So if you have any questions, please type them into the question area, and we'll take them as they come in while we're going through the rest of the presentation here.
Yeah, no, that means I need to hurry up. So again with inputting, if you have heading, depth, pitch roll, or a location, a position, you can input it here. I don't really bother with that for most applications, but it depends entirely on what you're doing. So next slide, output types. Every single time you set up a scan, click start scan, it runs and actually does the scan, you're going to get 3 files output. The 3 files are a .son, similar to the 2D, or same as the 2D, a .xyzi, which is your main point cloud file, and then a text file, which actually just includes your parameters, whatever settings you specified. So you're always going to have 3 files coming out of ProScan. I say in red here, this is the most important, just because this is the raw record of the data. Without this, there's no regenerating of the point cloud, there's no changing of settings, there's nothing. So this is the biggest file by far, because it is that raw sonar record. So if you have the hard drive space, which hard drive space is cheap nowadays, recommend keeping all your .son files if you can, just so you have the option to play it back as needed. And then XYZI is really what people want ultimately is their deliverable. This is the actual point cloud file. Standard format, it's not BlueView or Teledyne proprietary. It's a format accepted by many post-processing software or survey software packages, with just simply an X, Y, and a Z position, and the I is for intensity. So just the intensity of that return, or the intensity of that point, rather. So pretty basic file.
If you ever have any troubleshooting questions on a BV5000, the first thing we'll ask for is probably the .son file to review data, because then we can reprocess it and generate a new XYZ file and just check all the settings and everything from the scan itself.
Yeah, that's a very good point to bring up. We do generally always want to request the raw data to look at. Let me really quickly talk about BlueViewer. I know this is a ProScan presentation, but BlueViewer is in a lot of ways a part of ProScan. So this is our point cloud viewing tool. Very simple, very lightweight, very easy to send to anyone who you want to actually look at the data rather than, excuse me, rather than a fly through or a screenshot. Having the ability to actually pan around, zoom in, really look at the data is beneficial. So that's where BlueViewer comes in. I think it's downloadable on our website. Might be wrong, but again, it's free software.
Yeah.
Free software. It should pop up every time you complete a scan. It automatically comes up and says, here's your point cloud. So while in the field, it serves as a great verification tool. Okay, my tripod's in the right place. Usually in the field, I'm not getting in here and trying to take measurements unless it's critical to what I'm doing. Usually I just use it as kind of a visual verification tool. This looks good. Let's move on to the next scan or the next location. So a few things in BlueViewer. There's not much. Again, it's simply a viewer. We're not editing. We're not registering point clouds. We're not doing any modeling of any sort. We do have the ability to measure. We can see up here in the left, just a simple ruler function. So if I wanted to, I could measure point to point. So, quick, easy measurement, 3.78 meters. Might be good for just quick spot measurements. Not really of any extreme accuracy, but just a good tool to have. We have a camera pivot tool. So this little crosshair, if I do want to change my camera pivot, meaning the point at which my camera rotates around is I left click. If I want to, for example, look at these pilings up close, I can double click on the piling. And now my camera pivot is on this object. So helps if you really want to focus in on an object. The shopping cart down here, I can kind of get a closer look at. I can even do a measurement of, say, the bottom of the shopping cart. Whoops. So important to know that you have that option of changing the pivot. Really, that's it. To be honest, you do have a couple ways. You can look along the x-axis, look along the y-axis, look along the z-axis. Other than that, there's not much else to it. There are options for, if I double click on the point cloud here on the left, I can change the color map a bit. This might have benefit to some, but really I just keep the default coloring. And again, it's a review tool. So I'm doing a lot of the heavy lifting with regards to the point cloud in Quick Stitch, in Cloud Compare, or like a Cyclone software. This is really just a quick review tool. So
and it's also good for displaying the final data set. So we'll go through next week Quick Stitch on the processes of cleaning data and co-registering points, 2 point clouds together. And then once you have that final product, the BlueViewer is a great tool to easily email the program and the point cloud to a customer or anybody who wants to just display the data or view it and take these simple measurements as well.
Yeah, and that's all personal preference. My preference, BlueViewer actually generates some of the best looking point cloud imagery of any software I've used. So I do actually like to use it for screenshots and things like that. It just has a really nice way of rendering the points and giving you a nice looking point cloud. Okay, I just have one kind of exercise here at the end. I think it's actually quite important. Are there any questions? Should we try to tackle that now, or?
No, I'd say go ahead and go into your. Okay. You're gonna do the Japan.
Yeah, the Japan
process. Yeah. Yep. So as we're wrapping up, guys, everybody on the call, if you have any questions, feel free to type them in, and if you want to stick around, we're gonna do a little reprocessing of data exercise with this example here for a few minutes.
Yep. Yeah, so we went over this last week. Again, something John, you were on this, right?
That's right.
Yeah, you deployed very shallow river in Japan. They were looking for scouring along this structure here, this wall. They used this kind of custom tripod to get the sonar nice and low. Again, it was maybe 2 feet deep or less, something like that. So very shallow river. So we're going to look at this actual raw data that was collected during this little survey. So this would have been exactly what John or whoever else was there would have seen during acquisition, was basically this ProScan view. So I am playing now. We don't see much. We do see the image updating, but but we can immediately see this is very shallow. This is very noisy. It's a river. Rivers typically a lot of sediment, particulate floating around, high turbidity. So very noisy environment. And we can tell that just from the raw 2D imagery here. First thing I want to do here is actually just bring in the maximum range. If I were to drag the slider, we can see there's really no reason to have any range beyond 15 meters. We're really not looking at much. You know, during acquisition, they very well could have decreased the range to increase your ping rate because they didn't need to be looking the max 30 meters. You know, that's okay. I won't fault John for that. He was much younger then. But yeah, they didn't really need to have a max 30 meter range on this little scan because they were really only looking in a, say, a 10, 15 meter radius around the sonar. So first thing I would do in playing back the software is just bring that in because we don't care about anything beyond 15 meters. So let's set this to 15.8 meters. And now we get a much closer look. We're kind of zoomed in. So as I hit play again, we can see a few things here. We can see the river bottom. We can see how incredibly shallow it is. We can see the wall itself here. Actually, what we're interested in, we can see right here. Right immediately, right off the bat, if I pause it, we can see something suspect. We can see the wall and we can see just a gap underneath it, just a complete lack of wall at the bottom where it hits the river bottom. So immediately that's kind of an alarming sign at potential scour just from the raw data, not from the point cloud at all. So again, the raw data can give you some benefit just by really looking at it, and we can see here there's something that's suspect that we'll look closer into the point cloud. If I were to click scan and click start playback without doing absolutely anything, or if I were in the field and just clicked scan without changing any settings at all, just as it is right now, I would get the following point cloud. So we just did a scan in this river in Japan, and my point cloud is basically going to look like this. So not great. We can see the bottom, we can see the wall kind of. We have a few hundred points in the wall, but not much. Otherwise, we see all of this particulate, all this sediment just essentially blinding the sonar.
So why aren't we seeing the wall? What is causing us not to see the wall in this example?
Well, that's a good question. And it's really just comes back to the ranges. So we're doing one detection per beam, right? So in this case, the strongest detection along each one of these beams is actually on this floating sediment or whatever it is. I assume it was quite large to be picked up, but
it was actually aeration. So it was bubbles.
Oh,
Flowing by, because just upriver was a little bit, it was rocky, so it was really roughly flowing, and it was causing aeration in the water, which is a really good acoustic return.
Yeah, aeration is the enemy of the sonar. Yeah, that makes sense. So bubbles in the air are going to have a very strong, in the water are going to have a very strong return. In this case, we're only doing one detection per beam, so we're picking points on the air in the water, not on the wall. So a few things we could do to address this. I'm sure a lot of you probably right off the bat were thinking, okay, well, we should do 2 detections per beam, in which case we would capture, or maybe even 3 or 4 detections, in which case we would capture the air as well as the wall. We could absolutely do that. There is a better way though. We can use the intensity threshold. We can increase this to like 2,500. But that actually won't really do much, right? Because the bubbles are actually have a very strong return. So increasing it by that much will probably eliminate returns from the bubbles, points on the bubbles, but actually also eliminate any points or most points on the wall itself. So maybe not the best option. The actual best option is kind of great in its simplicity because it's essentially increasing the start range here. So let me zoom in. So I'm just gonna kind of put a magnifying glass on the data so we can actually see pretty clearly all the little white dots. That's the point picking on the aeration in the water. So we're seeing just all these detections coming up right near the sonar head. Now, if I decrease the start range, this is basically saying to the software, okay, don't ignore all points up until, in this case, 0.4 meters, or I can increase this up to 2 meters. Ignore all points from the sonar, from the transducer, 2 meters out. And we can see that actually represented by the software here. As I increase the start range, we're actually starting to ignore all those points and kind of push that barrier out to where we're actually starting to look for points. So if we, and this is common in certainly most river surveys, but really just surveys in general with the BV 5000, you really don't care about the first meter, 2, 3, 4 meters in front of the sonar a lot of times, unless you're in a really tight area. So a lot of times I'll really just ignore the first few meters because it's probably just going to be noise near the sonar head. In this extreme case, yeah, go ahead.
And you can use a combination of the range. I call this range gating. So we increase the start range to eliminate the points in the foreground. And then if you get to a point where you say, oh, well, I want that data, well, then you can also increase the intensity threshold, say just go up to 500 to try and eliminate some more of that noise in the foreground, but still selecting the correct points on the wall itself. So you can always do a combination of adding multiple detections and intensity threshold changes and range gate changes, and reprocess that data set 10 times with different settings and overlay them on top of each other to get the final deliverable that you want in the end.
Yeah, and that's really, again, the benefit of having the raw data is you can just rerun it over and over again, especially if you're a new user. Best way to familiarize with this range gating, with the threshold settings, is to just kind of rerun the same point cloud, or sorry, the same .son file, and just see how the results are represented in the point cloud. So here I'm going to increase the start range to, let's see, let me just go through here. So we can see the wall on the left. So the wall doesn't really get much closer than about, there it starts to go back again. So it doesn't get much closer than about, let me use my little measurement tool here. We can see in the lower right of the screen down here, this is another little tool. We can actually get a distance and bearing based on where our crosshair is. So we can see the wall here is at about 9.5 meters. So really I can theoretically set the start range to maybe 9 meters and that will just capture the wall. But I actually want to capture some of the river bottom before the wall. So I'm actually going to leave this at, we'll say 6 meters. I can even do 5. Really, most of the aeration is in the first few meters. So as long as I'm beyond that, I'm going to get a much cleaner point cloud. So I've only changed that. I'm not going to change anything else. Of course, if my sound speed was wrong, I could correct it here. It is right here. It's very cold water, I believe, 1434 meters per second. So if I were to click scan, I can rename it here, river scour with min range gate, something like that. Click start playback. I would get the resulting point cloud. So if we were to compare this with the other point cloud, which is right here, we're getting very different results. So, we're ignoring all of the aeration. We are cutting out a bit of the kind of river bottom close to the sonar head, but again, we think about the application. We don't really even care about the river bottom. We care about where the wall meets the river bottom and whether or not there's scour there. So just looking from a top-down view, we can see there's quite a clear indication of scour. We can see a lot of points picked beyond the wall, and if we kind of zoom down or pan down and zoom in a bit, we can really kind of see there's a gap below the wall, just an entirely missing piece of the wall, presumably from scour. The quick moving river is just cutting away at the bottom of this older wall. And so that's as clear of indication as we're going to get that we didn't otherwise see with the original point cloud. So
And you can always overlay this image point cloud with the other point cloud, so that you have a full coverage of the riverbed as well.
Yeah, that's a good point. So I can do that here. I just basically can drag and drop the other point cloud and it will put them together. So
there you go.
Good point. Yeah, so that's what they wanted. In fact, we can, even in BlueViewer, we can do a measurement here of how deep the scour goes. Let's say there. So again, ballpark measurement, but about 1 3/4 meters cut on the scour, and that's enough for the end user to basically go in, okay, we need to repair the wall, we need to send a diver maybe to further inspect if possible. In this case, it was hard for a diver just given how cold the water was, how fast the river was moving. So this gives us a very clear picture of what's going on. So don't always be discouraged by your immediate results. They might be kind of messy and noisy and not really give you the data you were hoping to achieve, but with just some simple setting changes in ProScan, we can really kind of zero in on what we're trying to look at. And then further with Quick Stitch or with our point cloud post-processing, we can do even more to really clean out a lot of the noise and improve the point cloud, change colors of the points, and really highlight what we want to highlight.
And to re-highlight Tyler's point from the beginning, the end result is the 3D point cloud, but there's a lot of value in just being able to see the raw image, real-time image. So you can see that wall in the acoustic data. So if you can see it in the acoustic data, we can make a point cloud out of it.
Yeah, so good to train your eye to know what you're looking at, even watching this while it's scanning. When you're doing a live scan, you'll actually see this live view as it's panning, kind of helps you assess the environment further than just looking at the point cloud. So yeah, I think that's...
Yeah, I think, we're going to call it here to respect everybody's time. We went a little bit over, and thanks for joining everybody that stuck around. If you have any questions, do you have our contact slide, Tyler?
Oh yeah, that's important, I suppose.
Here's our contact information. If you have any other questions and want to get in touch with us directly, that's our information.
Yep.
Great. Thanks, John. Thanks, Tyler. And thanks to everyone that attended. And hopefully you can join us next week, where we're going to get more into the point cloud post-processing, as Tyler and John mentioned. So thanks everyone for their time, and have a great day, evening. Take care.
Thanks everyone.
Take care, everybody. Bye-bye.